Atomic Energy Central School, Mysore presents physics practicals for class 11, academic year 2020-21. Experiment number 5, Hooke's Law apparatus. Good morning, my dear students of Atomic Energy Central Schools in India. I am P. Saravanan, PGT Physics, Atomic Energy Central School, Mysore. I am very proud to present you an experiment for class 11 in physics. The name of the experiment is Hooke's Law apparatus, and the aim of the experiment is to determine the spring constant of a helical spring from load versus extension graph. So yes, helical spring will be like this. It is a spiral spring. It is having several circular turns and it is stretchable. So whenever we stretch it, its length increases. That is called as extension of the spring. Suppose if the spring is made up of different materials, say copper spring, aluminium, steel, though they have the same number of turns, though they have the same dimensions like the length and area of cross section, the spring constants will be different. Actually, in the theory we have studied, what is meant by spring constant? It is nothing than the force constant of the spring. Spring constant is nothing but the force constant. Again, what do you mean by force constant? It is the force required to produce unit displacement. Look here, I will hold one end of the spring like this. I will stretch the bottom. So when I pull it, can you see that the length is increasing centimeter by centimeter? So for every 1 centimeter, how much force is required? That is Newton per centimeter. Similarly, for 1 meter extension of the spring, how much force is required? Suppose if I want to stretch this and extension should be 1 meter. Corresponding to 1 meter extension, how much force I have to apply? That only is called as the force constant, and that only is called the spring constant. Have you got it? Have you got it, my dear students? Spring constant is nothing but force constant. Force constant is again defined as the force required to produce unit displacement. If the SI unit of force is Newton and the SI unit of extension or length is in meter, can you guess what is the unit of this force constant or spring constant? Yes, it is Newton per meter. It is Newton per meter. Okay, what is the use of studying this force constant? Why we should study the force constant or the spring constant of different materials? Where do we use such springs first of all? One best example is such springs are used as shock absorbers in the two-wheelers and the four-wheelers. Am I right? Whenever you are going very fast on the national highways and suddenly at a short distance you are noticing a speed breaker, you apply brakes, or sometimes without noticing that you pass on over the speed breaker. At that time, if there is no suspension spring below the seat wheels, we will be damaged. So in order to avoid such damages, these suspension springs are used. Okay. Then how do we connect the bogies of the railway coaches? When railway coaches are connected, okay, one with the other one, we use some springs. Okay. So like this, the springs are used in several applications in our everyday life. Now we are going to perform the experiment. So once again I want to remind you, my dear students, the aim of the experiment is to determine the spring constant of a helical spring. The shape is called as a helical spring. Okay. Now you can see that the spring is provided at the bottom one weight hanger. There is a weight hanger. Here we are going to attach some slotted weights. So slotted weights will be like this. This is called a slotted weight. Why it is called a slotted weight? Because each portion of this weight is provided with a slot. Can you see one slot? This is a slot. Slot means what? It is a cut portion from any body. So if you take a circular mass and you cut a small portion out of it, then it is called a slotted weight. And it is 50 gram weight. It is 50 gram weight. and this can be attached or detached from a weight hanger. This is called this hook, okay? This hook is called a weight hanger because in this hook only all these slotted weights are hanging. So if I want to attach means the neck portion of this hook is provided with a sharp entry. So through that the narrow sharp entry I can either attach this weight. Suppose if I want to detach this weight also through the same narrow neck of the hook, I can either attach or detach these weights. Can you all understand how to attach and detach the weights? Now final portion you see which is not detachable. It is not detachable. Permanently fixed to the bottom. So this hook and the bottom slot together is 50 gram weight, and this is called a dead load. This is called a dead load. Why it is called dead? Because you can neither detach this or attach this. That is why it is called a dead load. Dead load is also 50 gram weight. So this gram weight, if you multiply it by 9.8 means then it will be corresponding to some other unit. So this gram weight can be first converted into kilogram weight. How? By dividing by 1000. When you convert this gram weight into kilogram weight and then multiply it by the acceleration due to gravity 9.8 meter per second square or roughly 10 meter per second square, then you will get what the unit as Newton. Understand that? Because 1 kilogram weight is also equal to 9.8 Newton. 1 kg weight is equal to how much? 9.8 Newton. Roughly we can call it as 10 Newton for our practicals. Okay, my dear students, are you ready for the practicals? Shall we explain how to do the experiment? Yes, students, welcome. This is the experimental apparatus required to verify Hooke's law. This is the spring called helical spring. This spring is attached from a vertical support, and the support is again fixed to a metal stand. This is a metal stand. The bottom end, that is the free end of the spring, is having a weight hanger, and there is a pointer. Can you all see the pointer? This pointer is going to slide over the scale. Take care that the pointer should not touch the scale. It will slide, but it should not be in contact with the scale to avoid the friction. Okay. Now, in this bottom hook or hanger, I am going to attach some slotted weights. I told you this type of 50 gram weights I am going to first attach. Okay. Where in this slotted weight hanger, this is called a weight hanger. So the bottom piece and this hook together is called the dead load. Okay. So first I have to start the experiment by attaching this dead load at the bottom of the spring. Okay. Before doing the experiment, one point I want to recall. The spring should be brought to the elastic mood. Understand that? Directly we should not begin the experiment. What is meant by bringing the spring to an elastic mode? First, without taking the readings, we have to attach 50, 100, 150, 200, 250, like that in gram weights we have to add. Then again we have to remove this. That is called detaching the load. Adding or attaching the load first, followed by detaching the load. 2-3 times you have to do. Then only the spring will come to an elastic mood. Just like when athletes before performing the 100-meter sprint or the 4x100-meter relay, they will do the practice. Have you ever seen on the tracks? Some few meters they will run very fast, and then again and again they will practice, so that the mood, okay, that athletic mood they will gain. In the same way, the spring also should be brought to the elastic mood. But I have already done it. Okay, I have already done it. Now the spring is ready for the experiment. Are you ready? Okay. Okay, students, welcome back. Now I am going to perform the experiment using the helical spring. You can see that the helical spring is attached from a vertical support. The bottom end of the spring is provided with a pointer here. This pointer is going to slide over a vertical scale which is calibrated in centimeter as well as millimeter. Now the initial reading of the pointer is 13.2 centimeter. There is no load attached to the bottom of the spring. In such a situation, first I will have to make a tabular column which I showed you before, which was available on the board. Once again, I tell you, you will have to make a notebook, that is to record the observations, that is observation notebook. As per the tabular column which I showed you, the serial number, the mass in kilograms and the load in Newton, the position of the pointer has to be noted while the loads are attached first, next followed by detached next, and the mean value of the reading we have to note down in another column, followed by the extension L in centimeter and meter in separate columns. So first the initial reading shown by the pointer is 13.2, and now I am going to attach the dead load. The dead load is 50 gram weight. Okay, the dead load is 50 gram weight. You can see that 50 gram weight, and it is attached first. This is called as a dead load. So note down the pointer has now slided down because of the extension of the spring in the downward direction. From 13.2, now the pointer has slided to 13.4. So this 13.4 centimeter has to be recorded. Understand? So it is recorded. After that, what we have to do is another 50 gram mass, okay, 50 gram weight. So this has to be attached. This has to be attached along with the dead load. So now totally how much is there along with the dead load? 50 gram weight is added. And now you have to locate the position of the pointer. So the position of the pointer is found to be 13.9. It is around 13.9. Okay. Next, another slotted weight of 50 gram. Okay, 50 gram weight is attached. So once again the slider, okay, the slider or the pointer below the spring will be stretched down, so that its position has changed from 13.9 to 15.8. Now the reading is 15.8. So like this, what you have to do is continuously you have to add in steps of 50 gram weight. Okay students, so now in addition to dead load, only 250 gram weights I have added. Like this, now two more I am going to add. Okay. My dear students, now three readings we have taken. One is for the dead load. For the dead load, the extension, no, that is the reading of the pointer was 13.4. Next it was with the 50 gram weight it was 13.9, and then with 100 gram weight it was 15.8. Now I am going to add another 50 gram weight. So when I add another 50 gram weight, it is stretched further, and the new extension, the new reading of the pointer is 18.9. Now it is 18.9. I have noted it in that column. I will show you later. Okay. Next, I am going to add dead load plus 200. In addition to the dead load, now 200. I have added 200 gram weight. And corresponding to 200 gram weight, the reading of the pointer is showing 22 centimeter. I have noted 22 centimeter. And lastly, one more 50 gram weight I am adding. So that dead load plus 250. You can see that the spring is proportionately stretched downwards. Look at the pointer's position. For 200 gram weight, it is showing 25.2 centimeter. Yes, students, are you all understanding? We started initially with the dead load. Then, in addition to the dead load, we added first 50 gram weight, and the corresponding reading of the pointer was noted. Then, we added 100. Totally, dead load plus 100. Then, followed by 150, 200, up to 250. Now, care should be taken that the experiment should be done within the elastic limit. Beyond 250, let us not do, because we need 5 points at least to plot the graph. In addition to dead load, 550 gram weight you add. Please don't go beyond the limit. So, elastic limit you must have studied. It is defined as the maximum limit beyond which the body will be permanently deformed. That means it cannot regain its original state, though it is elastic. Understand? So, up to 250 gram weight we have done. So, I have noted the readings under the column loading. Now, the same should be repeated. Unloading. In the loading column, we started from the dead load and ended with the 250 gram weight. Now, the reverse we are going to note down. So, the last reading will be repeated again in the next column. The last reading will be repeated in the next column, that is unloading. So, what is the first reading in the unloading is the last reading of the loading column will be the first reading in the unloading column. Understand? Same reading only will be written on the right side. I will show you by writing on the board. Okay. Now, I write 25.2 centimeter as the first reading across 250 gram weight. Then I am going to remove 50 gram weight. You please notice the pointer. All of you will notice the pointer when I remove 50 gram weight. What happens? The pointer is coming back to its original position. I find that now also the pointer is reading 22. The pointer is reading 22 centimeter. So across 200 gram weight, under the column unloading, I have noted 22. Then I detach another 50 gram weight. So another 50 gram weight is detached, so that now what is remaining in that hook is dead load plus 150. Therefore, across 150 gram weight, I am noting down it is found again 18.9. While loading also it was 18.9. While unloading also I find it to be 18.9. Suppose if it is other than 18.9, you note it down, no problem, because we are going to take the average of the extension produced during loading and unloading. Now what is the procedure you can guess? Another 50 gram weight I am removing. So that dead load plus 100. So under the unloading column, across 100 gram weight, I am noting down the pointer reading is 15.8. Are you understanding, my dear students? Are you understanding? What next you are expecting? Again the remaining 3 I am going to remove. Okay? Okay students. Now there are only 2 more slotted weights in the weight hanger. I am going to remove 150 gram slotted weight. Okay? I have removed now. So that dead load plus 50 gram weight is there, and the reading corresponding to this 50 gram weight, I find it to be 13.9 again. So I have noted it down. I have noted it in the observation notebook. Then one more 50 gram weight when I remove. I have removed that also. Only with the dead load. Only with the dead load, I find that the reading of the pointer is 13.4 centimeter. So what I have done here, I am going to show you by writing it clearly on the board. All my observations I am going to show you. Before that, you must know one thing. This is done in the physics lab with a camera at 4 meter distance away from the actual apparatus. I am very close to the apparatus and I am noting down the reading without any parallax error. So whatever is my observation, I have noted in the observation table. But in the camera, when you see, slight variations will be visible. So don't worry about it. In the actual lab, when you do, you will be very close to the apparatus only, so that there will be no parallax error. Can you understand that? Because of the distance of the camera from this apparatus, there will be a slight parallax error. Okay? So we will avoid that only when you do it practically in the physics lab. My observation is very correct because I am very close to the scale I am vertically viewing the pointer without any parallax. I hope you must have understood. I am going to write all the observations on the board. Are you ready? Okay students, let us write on the board now. Yes, all of you will look at the board now. I have made a tabular column. Like this, you are supposed to make a tabular column in your observation notebook. And what are the columns here? You have to note down. You see here, the first column is serial number. 5 to 6 observations you can take, beyond which it will cross the elastic limit. Second one is, we actually attached and detached the mass in terms of gram weight. 50s in multiples of 50s. So I am expressing the same in SI unit, that is in kilogram. So how will you convert 50 gram into kilogram? It is 50 divided by 1000 or 5 divided by 100. So in kilogram I have expressed, that is SI unit. Okay, so initially dead load is 0. Then 50 gram in kilogram, if you convert means it is 0.05 and 100 gram is 0.1. Like that 150 gram, 200 gram and 250 gram, they must be divided by 1000 and it should be written like this: 0 kg, 0.05 kg, 0.1 kg, 0.15 kg, 0.20 kg and 0.25 kilogram. Now I said 1 kilogram weight. 1 kilogram weight is also equal to how much Newton? I said 9.8. Okay, that is for theory calculations. Now practical calculations for plotting the graphical points. We can assume acceleration due to gravity g equal to 10 meter per second square. Okay, instead of 9.8, I will assume g equal to 10 meter per second square, so that for plotting the graph it will be easier. So I have multiplied this kilogram into 10, so that the unit is now Newton. It is Newton. So this is called as a load or W. Symbol is F, because the load is nothing but the weight and the weight is nothing but the applied force. So I can use any symbol, either W or F. So that the load is now converted from gram weight to kilogram weight, now kilogram weight to Newton. So this is 0 Newton and this is 0.5 Newton, 1 Newton, 1.5 Newton, 2 Newton and 2.5 Newton. So that for plotting the graph and choosing the scale, it will be much comfortable for us. I told you, my dear students, when you actually do the experiment, you will be standing very close to the pointer and you have to note down the readings. So whatever readings I have taken today, I have put up in the tabular column. So with the dead load, what is the reading or the position of the pointer tip? The position of the pointer tip, what number it was showing? For dead load it was 13.4. Then after attaching every 50 gram weight, it was extended. The spring was stretched down and the pointer was showing some other readings. So I have recorded under the column loading. When I added the gram weights, it is showing different readings and they have been recorded as X centimeter. Okay. So X is the reading of the pointer below the spring and its reading is expressed in centimeter. So that during the loading, the value of X respectively, starting from dead load, it is 13.4, 13.9 for 50 gram, 15.8 for 100 gram, 18.9 for 150 gram, 22 for 200 gram and 25.2 for 250 gram. I said not more than this 250 gram weight. So under the loading column, we have noted the extension or the pointer reading as X. Again I told you, we will detach the loads in equal steps of 50. Understand? So I start with now the last reading, namely 25.2, for which load, that is 2.5 Newton, that is 250 gram weight. Then every 50 gram weight when I removed, I have noted the pointer readings now, respectively 22, 18.9, 15.8, 13.9 and 13.4. Here absolutely I find that while loading and unloading, the pointer has shown the same reading. Sometimes by millimeters it may differ. That is why under the unloading column, the pointer reading is denoted with the symbol Y in centimeter. So under the loading column, it is denoted by X in centimeter. Under the unloading column, the pointer reading is now denoted by small y symbol. Okay, that also in centimeter. So that x plus y divided by 2 will give you the average reading of the pointer. But here I find that x and y are same. That is why the average of the two same numbers, okay, must be the same. So here, can you see the mean column? This is the mean value of the pointer reading. The mean value of the pointer reading is found by what? Z equal to x plus y divided by 2. So I am going to explain on the board some information. First one is, you see here the mass. So the mass M is equal to 50 gram. So this is equal to 50 divided by 1000 in kilogram. Is it not? 50 divided by 1000 in kilogram. So that it is equal to, this is equal to 0.05 kilogram. So this is a kilogram weight. 0.05 kilogram weight. And now the corresponding weight are, this is the load. So this is equal to M into G. So for our convenience, G can be assumed as 10 meter per second square. So here G can be taken as 10 meters per second square. Because if you multiply by 9.8 means for plotting the graph, the points will not be clear. That is why even if I multiply by 10 also, the points will be proportionate only. It will not be a mistake. Okay. So corresponding to this now, this is equal to what? 0.05. Okay, multiplied by 10. And now the unit is what? Kilogram weight. 1 kilogram weight is equal to what? Now 10 Newton. Therefore, it is 0.05 kilogram into 10 Newton. So that only the decimal will be shifted. So that this will be what? You can see here 0.5 Newton. So W is equal to 0.5 Newton. Have you all understood? Okay. So this is actually the force. This is the applied force. This force per unit area only is called as the stress. Okay, that you will study in the theory. Now this is the weight or the force applied at the bottom of the spring. Then you see the pointer reading. Now for example, X for the dead load. Okay, for this reading itself, when the mass is 50 gram, for the mass 50 gram, you see here, it corresponds to what? 0.5 Newton. Okay, so for 0.5 Newton, this is corresponding to this, the value of X, what I have taken corresponding to this 13.9. So this is equal to what? 13.9 centimeter. And Y, the corresponding unloading value, Y, that also is what? 13.9 centimeter. So Y is also equal to what? 13.9 centimeter. Therefore, the mean value of X and Y, it is easy, no? Suppose if you get here 13.9 and here 14.1, when you add these two, it will be 28 divided by 2 is equal to 14.0 will come. But as I have got the same values of X and Y, now I find that mean Z is equal to X plus Y divided by 2, so that this is equal to what? 13.9 centimeter. Are you all understanding how to find the average? The mean of two numbers I have found. So in the mean column, you see here in the mean column, All the numbers x and y are same. That is why I have written 13.4 for the dead load, and for 50 gram weight it is 13.9, for 100 gram weight it is 15.8, 150 gram weight it is 18.9, 200 gram weight it is 22, and 250 gram weight it is 25.2. Have you understood? Now the next one is extremely important. How to find the extension? Extension. See here, the extension here how to find is, you compare the dead load with that of the 50 gram. With the dead load, the pointer reading was 13.4. When you add 50 gram weight, the pointer reading has increased. Increased to how much? 13.9, is it not? So the initial reading for dead load was 13.4. Now the reading of the pointer for 50 gram mass is 13.9. So by how much the extension has taken place? Yes, can you guess? It is the final reading of the pointer minus the initial reading. I hope you must have understood now. The final reading of the pointer with 50 gram weight is how much? 13.9. The initial reading of the pointer with the dead load is how much? 13.4. So this difference is called as the extension L. In centimeter first I will write, afterwards I will convert it into meter. So my dear students, the extension here corresponding to 50 gram weight is 13.9. You see here 13.9, okay, minus 13.4. What is it? For this you need not require a calculator, is it not? So 13.9 minus 13.4 is what? 0.5. Have you understood? 0.5. 0.5 means by 0.5 centimeter only the extension of the spring has taken place when you have added 50 gram weight. Understand? So this difference between these two only is 0.5. Understood? 0.5 centimeter. Now next, what is the extension corresponding to 100 gram weight? That means after attaching or after loading 100 gram weight, what is the pointer reading we have to find out? What is the mean value of the pointer reading is 15.8 for 100 gram weight. Understood? So with respect to the dead load always, every time when you find the extension, here the students are making mistake. The consecutive difference they are writing and say, sir, it is not coming like that. Don't worry. You need not worry. You always subtract the heavier load with respect to the dead load. So now for the second reading, that is for 100 gram weight, the mean extension is how much? Okay, the reading of the pointer is how much? 15.8. So I subtract. Okay, I subtract the dead load with respect to 100 gram weight. So 15.8 minus 13.4. So this time you see, my dear students, you see here this difference. So 15.8 minus 13.4. Okay, 15.8 minus 13.4 is how much I have written? It is 2.4. Have you understood? I hope you are understanding. Shall I proceed? Okay. Now what next you can guess? What next you can guess? The next load attached was what? 150 gram weight. So for 150 gram weight, what is the mean reading of the pointer I have written? 18.9. Is it not? Now I have to subtract this 13.4 from 18.9. Understand? I need not represent with arrow mark once again. Shall I? Okay, you see this time. So this difference 18.9 minus 13.4. So what is that difference has to be written across the 150 gram weight. So that is 5.5. Like that, you find out the difference between 22.0 and 13.4. That will give you the extension corresponding to 200 gram weight. So for 200 gram weight, what is the mean extension? L. It is in centimeter. It is 8.6 centimeter. Similarly, last reading is for 250 gram weight. For 250 gram weight, what is the mean extension? L. It is equal to 11.8. That is the last pointer reading minus initial pointer reading. Have you all understood, my dear students? That is good. So now I have represented the extension produced in the spring, each for every 50 gram weights. So for the dead load, the extension is 0, of course. We cannot compare the dead load with the same load. So the extension for the dead load will be 0. Have you understood? Then the mean extension for 50 gram weight is 0.5, 100 gram weight is 2.4, 150 gram weight it is 5.5, then 200 gram weight it is 8.6, 250 gram weight it is 11.8 in centimeter only. Is centimeter SI unit of length? Yes, what is the SI unit of length? Good, it is meter. So I am converting it into meter by multiplying by 10 power minus 2 or dividing the number by 100. Understand? Okay. So now I am going to multiply by 10 power minus 2, that's all. Same number you can return now. If you divide means you have got just the decimal places. Instead I am multiplying by 10 power minus 2 and the same number is appearing here also in meter. Don't worry, I have multiplied by 10 power minus 2. Only the unit has changed. Value remains the same. Understand? Okay, so it is 0.5 into 10 power minus 2 meter, 2.4 into 10 power minus 2 meter, 5.5 into 10 power minus 2 meter, and 8.6 into 10 power minus 2 meter. Last column is what? 11.8 into 10 power minus 2 meter. Have you all understood how to complete the tabular column? You will have to use scale and pencil only. Okay? Either on the left side or the right side page as instructed by your teacher. You make a tabular column neatly and take at least 5 readings in addition to the dead load, and you always better express in terms of SI unit, that is the force or the load in kilogram weight or Newton, and the extension is a meter. So that we have studied that F is proportional to X or F is equal to Kx. So the force applied and the extension produced are directly proportional to each other. Is it not? Just now we have seen in the spring. So the force exerted by the load attached to the spring and the extension produced in the spring will be directly proportional to each other. I am going to explain this once again. Okay. After that we have to plot a graph, because the aim of our experiment is to determine the spring constant of a spring. From which method? From the load versus extension graph. I am going to draw a graph by taking the load along the x-axis and the extension produced along the y-axis. Why not I take the reverse? This is because varying the load only is called as independent variable. It is independent variable. Load is called independent variable. Based on the load, who is changing is called what? Extension. Therefore, extension is called as what? A dependent variable. So you must very clearly know whether it is electronics experiment or electrical Ohm's law experiment or the spring experiment. The independent variable only must be taken along the x-axis, and the dependent variable, which depends on the independent variable, okay, which depends on the independent quantity, must be expressed in the y-axis. So my dear students, here the load is taken along the x-axis and its unit is Newton, okay, its unit is Newton, and the extension is taken along the y-axis and its unit is meter. So that the spring constant we are going to express in the units of Newton per meter in SI system. Are you ready for drawing the graph? If you have a graph means you keep it ready with you. I will show you how to plot the graph. Okay. Now experimental observation is over. We are going to plot a graph. So we have to take a graph sheet. And on the graph sheet you write the title. Then along the x-axis which quantity we are going to take. Namely load. Along the x-axis load in Newton. We have to mark. Then along the y-axis, the extension in centimeter or 10 power minus 2 meter. We are having the tabulations here. Is it not? The values are tabulated, you see, in Newton. So it starts from 0, then 0.5, 1 Newton, 1.5 Newton, 2 Newton and 2.5 Newton. You can take 1 centimeter width or 2 centimeters also if you want a neat and broad graph. Okay, but proportionately you split the x-axis as well as the y-axis. Now along the y-axis, how to choose I will tell you. Some mean extension, you see what is the minimum value is 0.5. What is the maximum value is 11.8. That means up to 12 only our graph will be accommodated. So 0 to 12 centimeter, at least 12 centimeter we must have in the y-axis or 24 centimeters. So now I have split the y-axis into 2 centimeter, 4, 6, 8, 10, 12 up to 14 I have shown. For us up to 12 only is sufficient, isn't that? Okay. Now how the graph will be looking? First I will show you the rough sketch of the graph, then the actual graph and calculation I am going to teach you. So the graph x-axis load in Newton, y-axis extension L in 10 power minus 2 meter are noted. So in any graph first of all you have to show the x and y axis, choose the x and y axis. Then the scale on this now, what scale we have taken, I am going to show you the actual graph now, okay? Roughly, what will be the nature of the points located on the graph I have shown now. This is a rough graph only, not the actual graph. So you will be having different points like this. Now I have to join these points. I am going to join these points. So the nature of the graph will be a straight line, understand, like this. This is a straight line. Why this is a straight line? Because the force F is proportional to the tension. Okay? The force F is directly proportional to the extension. Understand? So the load is directly proportional to the extension. It is a linear graph. So F is equal to what? F is equal to what? K into L. Where K is a constant. This K only is called as what? Force constant or spring constant. This is what at the beginning itself I told you. Spring constant K from this equation, K is equal to F by L. So this K is called spring constant, but it is defined as the force required to produce unit displacement or extension. So its unit must be what? Newton per meter in the SI system. Have you understood? So this value of K from this graph we have to find out. Sometimes when you plot a graph, one or 2 points, so one point may be above this, another point may be below this. Don't worry about it. Out of 5 observations, at least 3 observations will lie on the line. You need not worry. We have studied in mathematics y is equal to mx plus c. That is the equation of a straight line. Like that here F is equal to K times L is an equation of a straight line. Therefore we are getting a graph as a straight line. So on the straight line you choose any 2 suitable points. For example, I will say this point is A and this point is B. Understand that? I will project these points. I will project these points like this. Okay? I will project these points on the x-axis so that now you can see this separation delta x. This delta x is equal to what? Delta F. Okay? Delta F. So this difference between 1.5 Newton and 1 Newton is 0.5 Newton. So this can be taken as what? 0.5 Newton. Roughly I am doing that's all. Our actual value I am going to show you another graph. Actual graph I am going to show you now. Roughly. Okay. Similarly these 2 points. These 2 points are projected on the y-axis. Roughly. You see here for example, the y-axis separation is how much? 12 minus 8 is equal to what? 4. So this vertical separation is delta y-axis, and this is equal to what? This is equal to delta L, and this is equal to what? 12 minus 8. So this is 12 minus 8. That is 12 minus 8 is equal to what? To 4 into 10 power minus 2 meter. Have you all understood? Shall we go to the actual graph? Okay. Okay, now I am going to explain you how to draw the graph between load versus extension. So you take a fresh and a neat graph sheet. Over it, on the top you write the title like this: spring constant of a helical spring. Then you choose the suitable axis, that is load is taken along the x-axis and its unit is Newton. Extension L is taken along the y-axis and its unit is centimeter or 10 power minus 2 meter. Then for any graph there should be a perfect scale. Along the x-axis, what scale I have taken? Every 2 centimeter is equal to 0.5 Newton. You see here, 1, 2, 2 centimeter is equal to 0.5 Newton. Along the y-axis, what I have taken? Every 1 centimeter is equal to 10 power minus 2 meter. Have you understood how to choose the scale? Good. In our tabular column, we have taken 5 observations, totally 6 including the dead load. Leaving the dead load, the remaining 5 points I have plotted. You see here, the first point is the coordinates. The coordinates you can verify with the tabular column what you have taken. So for 0.5 Newton, the extension is 0.5. Then for 1 Newton, the extension is 2.4 into 10 power minus 2 meter. For 1.5 Newton load, the extension is 5.5 centimeter. For 2 Newton load, the extension is 8.6 centimeter. Then for 2.5 Newton load, the extension is 11.8 centimeter. So for every point neatly, you draw the coordinates in brackets so that it will be very clear for finding the slope or whatever information from the graph. This is the right way of drawing any graph, plotting the points with the x and y coordinates. Okay. If you join all these points, I find that only 4 points are coming on the straight line. The first point is away from the straight line, but I don't worry for that because maximum points are accommodated in the straight line. In this, any 2 points you choose. For example, I have chosen a point A whose coordinates are 1.5, 5.5, and another point B whose coordinates are 2, 8.6. And what is the separation along the y-axis? Okay, that is delta y. And the separation along the x-axis, that is delta x. They are mentioned as BC and AC respectively. So from this, how to find the spring constant, now I am going to explain on the board. Before going to the explanation, have you understood how to plot the points on this graph? Good. Now I will take you to the calculation on the board. Okay. Okay, students. I hope you must have understood how to plot a graph between the load and extension. Now, how to do the calculation from the graph. So this was the nature of our graph. From the graph, you choose any 2 convenient points. I have taken A and B from our original graph. The coordinates of A are 1.5 Newton and 5.5 into 10 power minus 2 meter. The coordinates of B are 2 Newton and 8.6 into 10 power minus 2 meter. So I project B vertically downward up to C and A is extended up to C, so that is a right triangle. Okay. Now the portion B to C is called the delta y-axis. The portion A to C is called the delta x-axis. So along the x-axis, what is the change in the reading between A and C is denoted by delta x, that is equal to final coordinate x minus initial coordinate along the x-axis. So it is 2 minus 1.5. So delta x is equal to what? 2 minus 1.5. That is equal to what? 0.5 Newton. And that is denoted as the force or load F. Along the y-axis, what is the change is called as what? Delta y. That is equal to what? 8.6 minus 5.5. That is equal to 3.1. And the unit is 10 power minus 2 meter. And that is denoted as the mean extension L. Already we have studied that the load is directly proportional to the extension, isn't it? F is proportional to L, or F is equal to what? K into L, or K is equal to F divided by L. This is another form of Hooke's law, that's all. Stress is proportional to the strain. You will study in the theory, I say. So, my dear students, F by L only we have to calculate, because the aim of the experiment is what? To study or determine the spring constant from a load versus extension graph. So in this graph, F by L will give you, that is a load versus extension ratio will give you the spring constant K. So instead of F, you substitute 0.5 Newton. Instead of L, you substitute 3.1 into 10 power minus 2 meter. Okay? Now this 10 power minus 2 is in the denominator. When it shifts to the numerator, it will become 10 power plus 2 or 100. So numerator is 0.5 into 100 divided by 3.1, and that is equal to 50 divided by 3.1. It is found to be 16.13 Newton per meter. Our calculation is over. That is also the value of the spring constant. Next, we have to summarize the value in the result column. That is the final column in any experiment. So the result. The spring constant of the given helical spring is K equal to 16.13 Newton per meter. Have you all understood? I hope you must have understood this experiment. Are you happy? We will see in the another experiment. Until then, bye. See you.